So, good evening, everyone. Welcome to week 6 of the live interactive session of Fundamentals of Micro and Nanofabrication. The course instructor is Professor Susovan Avasti and Professor Sankar Selvaraja from IIC Bangalore. I am the PMR of Teaching Assistant Vikas Pandey from IIT Jodhpur. This is a brief about me. This is the class link, the YouTube channel where you will find all these recordings and my contact details in case you need to contact me. So before starting the topic that is metallization and optical lithography, will just be starting optical lithography. I would like to ask if you have any questions, you can ask or we can discuss, and then we will move forward to the topic. Yes, any questions?
I'm having one question related to one last week that assignment.
Okay,
There's one. Just a minute, I will read out the question.
yeah,
Just how does the mean free path affect the directionality of metal atoms during evaporation?
okay,
So there were four options. That longer mean free path ensures more directional travel to the substrate.
hmm,
Shorter mean path uh, increases collision and scatter.
yes,
Mean free path has no effect on directionality of atom travel, and longer mean free path reduces the deposition rate.
okay. So,
So
what according to you should be the correct answer?
I think there are two correct answers. So there were no two options two for selecting. So I selected the shorter mean free path increases the collision and scatter.
But what is the question? Can you read out the
So
question?
how does the mean free path affect the directionality of metal atoms during evaporation?
Yeah. So longer shorter free path will increase the collision. That is correct. And
Right.
one more thing is that in fact we are increasing the mean free path for one single reason, that is directionality. Like if an atom is directed in one direction, it will continue to be in that direction without collision. So I think the first option you said, no,
Yeah.
that is also correct.
That's what I say. There are two options I feel correct, but
Hmm.
there were not options to select two options.
Okay. So what is the correct answer? Like now answers will be displayed, right?
Yeah. It is correct answer is the longer mean free path ensures the more directional travel to the substrate.
Yes. So other like the question, what I understand is that question is about directionality. Okay, and when we are selecting the third answer, that is third or second, no? Which is that it will increase collisions, shorter mean free path.
Mm-hmm.
In that, I think the discussion, although it is correct, that statement is correct, but that is not about directionality. It is not discussing anything about directionality. No?
Yes, scatter is about directionality, right? But if some atom is going
It's
and it is
yeah,
colliding
not
with the
not that.
some other
Yeah,
atoms, then it is about the directionality itself.
yeah, but not directly. So that may be the reason that sir has kept it like
Okay,
that.
no problem,
Yeah,
no problem. That
yeah.
just finding that whether that answer is also correct or not.
No, this is factually correct, but yes,
Mhm.
it will not have an effect on like it will have an effect on the directionality, but this answer is directly not mentioning what is asked in the question. That might be the reason that it is being
Okay,
not
okay,
considered as the right answer.
no
Yeah.
problem, no problem. Yeah,
Any
okay,
other
thank you.
questions?
No, thank you.
Yeah. Yes. Anyone else? Yeah. So let's move forward. Today we are starting a very very interesting topic, that is metallization, and then we will start a very important topic of this whole microfabrication thing, that is uh, lithography. Okay, and in fact, if you see the course curriculum, 3 weeks, like this topic lithography covers 3 weeks. It is very important part of micro and nanofabrication. Okay, So when we have discussed till now, we have discussed about uh, silicon dioxide, that was oxide. We have discussed about depositing different kind of layers, and in deposition of different kind of layers, we discussed about CVD and PVD, two different ways, right? And ALD was part of CVD, but a different way. MOCVD, that is for epitaxial growth. All these we have. But during this process, in many times we were discussing that this method is to deposit metals. This method is good for depositing dielectrics. Fine. So can anyone tell me which methods are good for metals? What we have discussed till now. What deposition methods are better suited for metals?
Is it PVD?
PVD have many processes, like many,
Sputter?
yeah. Sputtering is
Sput-
also used, yeah. Sputtering is used, but most commonly evaporation is better suited for normal metals. Sputtering is also used, correct? Yeah.
okay.
Any other methods? Yes. Anyone?
APCVD.
LPCVD is also used. And if we are going, Ajike, you said sputtering, right?
Yes.
So what kind of sputtering? Because sputtering we have studied two, three types. What sputtering will be used for metal deposition?
DC sputtering will work because yeah,
Yeah, this
so
is
the electric is not there, so we don't have any issue with the charging.
charging. Yeah, metals can be deposited using both uh, DC as well as RF.
RF.
Okay. Yeah, but non-metals cannot be deposited using DC sputtering.
DC, right?
Fine.
Right.
Yes, yes,
Yeah.
correct.
Okay. So uh, we have discussed about metals. We know how to deposit metals, but what are the different things that we have to consider when depositing metals, and what is the role of these metals? Why we need metals? And okay, so metals are generally used for contacts. Contacts mean conducting electricity simply to our devices. Okay, and if you see a modern device, there are multiple layers of metals. Like if you see this image, this is this wire, via, and these things. No? These are metal, all metal layers, and below is our small it, like the thickness shown here is very less for the substrate. So there are multiple layers of metallization for different connections, just like we do in case of PCB. Printed circuit boards, everyone is aware of.
Yes, yes.
Yes, yes, yes. Yeah.
Okay, so just like in PCB, there are multiple layers. Here, there are sometimes 200 or 300 layers of patterning, different patterns of metals and these oxides and all for a general processor that we use. Okay, so these modern devices require multiple layers of metals for efficient interconnects because we cannot directly have one layer. There we need different layers for different routing. Each layer serves different role for connection at lower layer to, to thicker, higher current pathway at upper layer. So it is not that if we have some metal at say 50 nanometer thick, that cannot carry very high current. For higher current, we will have to have thicker layers. For uh, but for connections, like we cannot have such thick layers at the lower level itself. Because we will see why very thick layers are not possible at lower level. What problems they give us. Okay, so that we will see. As well as we have studied about dielectrics and their deposition, and they are also important because we need insulation between layers. everything should not be shortened. So many times you will be depositing metal, you will be patterning, removing the area that we don't want, then again put some oxide layer or insulation or dielectric, then remove the areas that we don't want, keep using patterning and then etching, and then deposit another metal line. So it is a multi-step process. And why these insulations are important? They are important because they prevent electrical shorting, and they should be of such amount that they are able to, like, just yeah, okay. Insulators with low dielectric constant minimize capacitance and signal delay. So it is not that we put any kind of insulator in between uh, two different metal lines, because there is a very big problem that if there are two conducting layers and there is insulator in between, it acts like a, yes, anyone,
Capacitor.
a capacitor. Yeah. And if it acts like a capacitor, there will be charge storage and we will not be able to achieve our, like, when we are talking about metal lines, that means it should be conducting directly. There should be no charging or discharging. So it might act as a capacitor, and we don't want that. That's why the selection of insulator is also important, and so it should have low dielectric constant, that is low K material. Okay, so we have this two problems. One is, if we have high K material, that is high dielectric constant, we will make good capacitors. We don't want capacitive effect. And if we have uh, low K materials or low dielectric constant, in that case, actually there are chances of shorting, because they might not insulate that well. So there is a we have to like come up with a solution to counter these two. How much thickness should be there and all such optimization has to be done. So these are some images taken from the reference. You uh, anyway, share all the slides so you can check these references for more details. Like you can see how metal lines are there. This is a SEM image. Okay, so dielectric interconnect is there. That is to separate. These are metal lines, bigger lines, then followed by smaller. Like as we go deep, you see the size is decreasing layer by layer. So actually it is from bottom to up, and the topmost is the top layer where we will be taking contacts, but below is where our devices do exist. Okay. So what is the configuration of these metals? Okay. So the layer configuration is such that the bottom layer is the silicon substrate with devices. As I said, like if we see, it is, we have our silicon, and then we have, say, some devices using some material we have grown. Okay, like this. This is our device, or it might be planarized, not an issue. Okay, it will have some doping. We have learnt about doping. We have learnt about oxide growth and all these things. So this is the lowest layer. Okay, then we have first metal layer M1, that, say, is making contacts here. Okay, then we will have bigger layers, bigger than this, or maybe smaller than this, or interconnects and these things. And so that layer will be M2, and so from the bottom to top we increase M1, M2, M3, and they are connected. When we talk about dielectric, let me put some other color. Say here is a dielectric. We are filling it with dielectric. Okay. So they are connected using vias. The intermediate layer, like a tunnel kind of structure that connects one line to another, that is called as via. And as we go towards the upper layer, it is very thick. It's a thicker metal layer for high current pathways. Okay. And what is this insulating layer? SiO2 is commonly used, but its deposition must occur at low temperature to prevent metal diffusion, because we have seen that we know that metals actually can melt at a higher temperature and diffuse. So we cannot do silicon dioxide deposition using uh, like oxidation, not possible. Although we can deposit silicon dioxide using oxidation, but when we have done metallization, that is not possible. Even CVD, normal thermal CVD, not possible. We can go for some plasma enhanced CVD, or we can go for ALD, or best is we can go for this sputtering to deposit silicon dioxide also. So we have to take care that it must not, this deposition of silicon dioxide, if being used as the insulating material, it should not be deposited at higher temperature. Yes, Ajiket, you are saying something?
No, no. I was just thinking ki between sputtering and ALD, which is more lower temperature, because ALD we can do even room temperature or below room temperature also, right?
Yes, yes.
Sputtering should need some
Sputtering,
more temperature.
yeah, some more temperature, but like metals can sustain at least 70-80 degrees, so not an issue. Because sputtering, when we are doing, yes, you are right that some temperature rise will occur even if we are not giving any temperature, if it is being done for longer time.
Mhm.
But that much a metal can sustain 70-80 degrees. That's not an issue.
Okay, thank you.
Yeah. And ALD will actually be much costlier
Mm.
as well as time taking if you compare ALD and sputtering.
Right, right, right.
But the problem with the silicon dioxide is that lower temperature deposition actually leads to poor oxide quality. We want
Mm.
better oxide. So these are some things we have to take care while making this. Okay. Then is back-end processing. This refers to the steps after making the devices. Okay, that is the whole metallization part or metal patterning, whatever we are talking about, that comes under the back-end processing. Because our device is made, once our device is completely made, after that the metal deposition and interconnect formation, everything is considered as back-end processing. So we are talking about back-end processing when we are learning about metallization. Although the techniques that we will be uh, learning here, like lithography and all, which we will be learning just after this, that is also a part of the front end processing, that is making the devices. Like we have talked about creating masks for ion implantation and all, but we didn't learn how that mask is. We said that we'll just open a window and close all other places, that we have seen, and that process we will learn in case of lithography. So, but metal contacts and all these things, these are part of back-end processing. Okay. What are the challenges that we have to encounter? That this whole process has to be done at low temperature to prevent metal diffusion. Okay. And we cannot use cleaning methods that we have learned. That is RCA, not pos RCA, Piranha, they will etch everything. They are not good for metals. So specialized cleans are required, or we can go for a simple degreasing method like we talked about in the one of the classes where we were using uh, if it is not a very harsh, like it is a very tough stain or something, we can then go for a simple degreasing process involving acetone, IPA, and methanol. Okay, metal deposition process is delicate and requires handling to avoid structure damage, because you see it is not just a planar structure, it might have pillar kind of structures, right? You see, these are called vias. Okay, such pillar kind of contacts can be there, and they might be delicate to handle, as well as proper aligning has to be done. Otherwise, what will happen that suppose that it was to make contact here and it made contact with something else, or it didn't make a contact. So we have to take care of these things. These are key points that we have to consider while doing the backend processing. This is once the devices are made, the main device, like if we, let's consider transistors or something like that. Once they are done, then we have to consider this. Now we have seen what is the bigger picture, but let's come to some simple interfaces. So starting with metal silicon interface. Okay, so when we have silicon, mostly we are talking about silicon or any semiconductor, and when we deposit a metal over it, and when it comes in contact, so there is a gap between the phi m and phi s, that is the matching of this potential barrier can like it cannot have the same work function as this the semiconductor, and the metal will not have the same work function. Okay, so there will be some difference, and this difference leads to a barrier, small barrier of like conducting electrons or whatever charge we have. This stops the current flow, especially at the metal silicon junction. So you may have made a device that is not rectifying in nature. Say we have made a device which is like this, that it is N plus, and we have made a channel inside N plus, N plus. Okay, and here we have uh, P. It's a P-type substrate. Okay, so ideally, what we should sorry, what we should consider is that if we deposit a metal here, suppose we are depositing a metal here and here, it should be conducting fine. But due to this barrier, it might not happen. Okay, so there is a way that we have to minimize the phi b, that is the uh, difference in their work function, by matching the metal. It should not be that any metal is deposited on the surface. That's not possible. On if it is silicon, we have to take care what metal has to be deposited and how it has to be deposited. Okay, because we want that there should be no resistance due to this metal silicon interface. So if you see a simple this is these are graph of two of my devices. Okay, in one case what has happened is that you see that this one is a perfect contact where the metal layers are perfectly matched, and actually what we generally do is that we gradually make a difference, like if it is silicon, this not of silicon, this is some other material, silicon, so slightly like phi b should be very small for the next material, say let's say chromium, and then on the top we want to deposit gold, so we put gold. So when this difference is less and this difference is less, it will be gradually flowing properly, like that barrier will be very low, and overall we will get a ohmic kind of current like we are getting here. You see, uh, with voltage it is like growing gradually, no difference. But when sometimes we are making Schottky contact, purposefully also sometimes we make such contacts. Okay, so in this case you see it is rectifying in nature. So it is almost zero for some time, and then at once it increases a lot and the current shoots up. So it is a Schottky contact, like it needs the barrier to be broken for the conduction to happen. Fine. So how do we achieve these ohmic contacts? Are you getting my point, everyone?
Yes. Can you please explain the previous drawing which you made? The
Yeah.
No, one slide previous.
Okay. This one.
This one. The
Yeah. So I am saying that suppose that this is a hypothetical one. Certainly it will not be like this. That if we have n plus, n plus, and n plus. So all this is connected. So we have a path, a current path that should go like this, right? So
Mhm.
we should consider that if we are depositing a metal over this to n plus, we should get a current, flawless current, right? Like we should be able to conduct flawlessly. But if we are not matching this metal and like metal and silicon interface properly, we might not get what we want. And the reason can be due to the Schottky contact that we are creating. We might not be matching the work function or for this interface, and the potential barrier, that is phi b, can be larger. So we have to take care that phi b should be as small as possible.
Right. Yeah. But
Okay.
here N plus is already internally connected, right? So
Yeah, here it is this internally connected. So it should be simply a conductor kind of
correct.
behavior. But if this interface is not matched, although we have done all the device fabrication correct, this match this mismatching can result in some outcome that we don't want.
Right. Yes.
I think it is just making a diode kind of thing, right?
Yes, a diode kind of structure, and that also between metal and semiconductor, not
Semiconductor.
semi,
Yeah.
yeah, not semiconductor like we make purposefully. It is
Yeah.
where we don't want it to happen.
It's a like Schottky diode, what we are
Yeah,
learning. Yeah.
yeah, that's why it is called as Schottky contact, because it is
Yeah.
like a Schottky diode. So, yeah. So, how do we achieve this ohmic contact? Because ideally the contact should be ohmic, not Schottky. Okay. So we do metal work function adjustment. Like I said, one is we use metals which have closer work function, like where phi b is less, like aluminum and zirconium, and even chromium is used very frequently. Second is using passivation. Passive, when we passivate using silicon nitride or titanium nitride, TiN is used, that lowers the barrier height. Or it is also done is that highly doped silicon layers are used as the contact instead of metal as the first contact. Very highly doped silicon layer itself is used as the contact. So silicon and silicon will have no phi b, so conduction is very easy. And then later on, like we gradually connect it with metals. Okay, so the contact resistance will decrease, and as such we will have ohmic behavior. So it should ideally have uh, no resistance. It should have ideally no barrier. Okay, that is our aim. Okay, why this? I have changed it. Just a minute. I think this has not updated. Okay, anyway, leave it. Okay, there here one graph was to be put. I will put it. Okay, so sorry. So when we are talking about contact resistance, okay, contact resistance, how do we measure? Because the area can be different. Okay, so it is called in terms of specific contact resistivity. Okay, and it is shown by okay, and it is measured in terms of ohm centimeter square. Okay? This is resistance scaled by area. It ensures consistent resistance measurement across varying contact area. So it is not that if I am measuring the resistance for this device, someone else is measuring the same thing but at a in a larger area or something, it will have different contact resistivity. Like it should not have different resistance. It should have the same thing to be at the common platform. We are using specific contact resistivity. And what is the thing that defines it? It is influenced by doping level. Okay, higher doping, that means higher electron flow, will have reduced contact resistivity. And barrier height will also have an influence. Lower 5e results in lower contact resistivity. Okay, this graph I will put, that is the function of like function of doping for different metals, how it changes. I will put that. Okay, now there is another problem, that is silicides. When we are dealing with silicon, certainly silicon can have some reaction too. Okay, so that is one of the is everyone getting?
Yes, yes.
Okay, just a minute. I think some slides has not yet updated here. Let me just check. Sometimes it's just a minute. I think there is maybe some delay in this. Okay, it has one video, so that's why it's not loading. Let me do one thing. I will show the video on instead of this. I will show on a different device. So I think in that case it will show it. Okay. So the when we are talking, is the slide visible? Hello.
Yes, yes, visible
Yes.
slide.
Okay. So when we are talking about silicon and metals, there can be some reactions too. Okay, so silicides can form. That is an alloy forming between a metal and silicon upon annealing. So during this process of metallization, sometimes to quench the uh, metal lines, we do some kind of annealing, small like 100-150 degree. Okay, so there can be some silicide formation, that is alloy of metal and silicon, but it has some advantage also, and that is why we do this. That is, it reduces the contact resistance and provides stable and repeatable interfaces. That means, suppose that you are make depositing chromium and gold over silicon, and every time you are getting some different resistances. So what is generally done is that, let's say, in both the cases, we are annealing it at 150 degrees Celsius for 30 minutes. And then if you compare, the resistance will almost be comparable. We will not get different resistances because these silicides will form. Tit- uh, Titanium is one of the common metals with which silicides form. Okay. Tungsten also forms. Nickel, yeah, nickel is also there. Nickel, tungsten, titanium, such metals. Okay, yeah, it's given here. Yeah, so tungsten, it's highly stable and forms stable silicates at 600 to 700 degrees Celsius. In this case, you have to go to higher temperature. When nickel, low low formation temperature, that's 300 to 600 degrees Celsius, and is moderately stable. Nickel is in general used, if it is not annealed, it is generally used to create Schottky contacts. Okay. Now, one of the common material that is used in microfabrication, common metal, is aluminum. Okay. And what that is aluminum. So what happens in case of the aluminum silicon interface? Aluminum is highly soluble in the silicon, and this leads to silicon diffusion into aluminum. That is, you see, this area is visible where it is entering. Such spikes are formed. Okay, this causes the heating of the aluminum silicon interface, leading to silicon wires filled by aluminum. Okay, and this might lead to shorting of the PN junction, resulting in device failure. Some diffusion is fine, but if it is creating spikes inside, that can be a problem. So how is it prevented? A small, thin layer of titanium nitride can be used. This forms the this forms titanium uh, silicide formation. That is, aluminum will not diffuse into the silicon. Just a minute. Yes. Okay. And second problem is electromigration in metal lines. That is, the gradual movement of metal ions within a conductor due to momentum transfer from flow of electrons. This is commonly observed in metal lines with high current densities. If we are flowing very high current, like the current density is too high, then we can have something called as electromigration. And this can lead to voids, like you see here, the metal line looks like there is etched out kind of structure, or hillock, like metal getting like a lump formation. Okay, this leads to increase in resistance, circuit delay, and potential failure of our devices. This is very critical for reliability of the microfabricated devices because the device might be working fine, but the metal line is damaged. That's why we might not be getting our desired output. So, what is the mechanism of this electromigration? How it happens? There are two kind of mechanisms. One is diffusion mechanism, that is bulk diffusion or surface diffusion, and or grain boundary diffusion. Like, and what at what energy levels it happens? Bulk diffusion occurs at around 1.4 electron volt. Surface diffusion around 0.28 electron volt, and grain boundary diffusion at around half electron volt. Whereas there can be some electromigration due to grain boundary movement. That is, electron flow exert force on the grain boundary causing the atom migration. Grain boundary means when we have difference in the crystal or difference in uh, metal structure, two different metals and this thing. This this actually is having the same energy level as the grain boundary diffusion, that is half electron volt. How do we tackle this electromigration? It is tackled by making this like alloying, or you can say doping these metals. Like copper is mixed in aluminum. Adding 4% copper reduces electromigration by slowing down self-diffusion. Self-diffusion is lessened. Okay. As well as it has been observed that copper doped aluminum is taking longer time to fail. So that's better. Like we don't get electron migration there, less electromigration. Or there is another way, that is using high melting point metals, because this will only occur if uh, this electromigration leads to such temperatures where this metal will melt. That's why void or hillock will form. So we can use high melting point metals like tungsten and cobalt. Okay, or even tungsten silicides, molysilicides. They are also good way to. These are conductive. Okay, so they can also be used to mitigate electromigration. Second is grain. Uh, second reason is grain size and geometry effect. Large columnar grain, like column kind of structure, they reduce the vertical component of force and minimize the atom displacement. Whereas if we have small random grains, that increase the risk of voids formation due to vertical force component. So one way is using large columnar grains. Second is we can use geometry. Thicker lines, that means more grain. We will, if we have thicker lines, that will have more redundancy. Like if some part is failed, even then some other part will work. So there will be lower risk of failure. Whereas if we have thinner lines, we have fewer grains and high risk of critical grain displacement leading to failure. That's why you see that there are some devices, electronic devices, if you buy, they will not work reliably for longer time. The, yeah, there's what you say, but there can have been some cost cutting. Generally, some Chinese companies and all, they are making this perfect. They are having some cost cutting, reducing the thickness, and this can have some effect in the long run. That may not lead to good quality of conduction. Okay. Then is another solution, that is design solution. That is one is cladding. Cladding is just like we do cladding in case of our home wires, that we cover it with some insulating materials. So one simple way here, we are not using insulating material directly. One is titanium cladding. That means internally we are flowing current through, say, aluminum, but on the top of it, on it, we are putting a layer of titanium. So if heat occurs, the upper layer will protect, because the upper is not going to melt at such low temperatures like aluminum is melting. And in that case, if even if the line fails, the current might decrease, but it will flow through titanium. Second is reservoirs in well lines. That means, suppose that these points have to be connected, and they are connected through such metal lines. Okay. Then another metal line like this, we have kept it, and in case this path fails, we can connect this path and we can get our current. So such redundant extra line, we might run a parallel line with this, so that if this first path fails, the second path will work. Okay. This minimizes resistance and increases the time to fail, because one line can fail but all the lines fail the same. So such redundant metal or reservoirs are used to counter this problem. Now the second thing is that aluminum was the most common one earlier. Okay. Now microfabrication is moving towards copper metal lines. Still here any? Oh,
No.
yeah. So the aluminum had the advantage that it was low cost, which it worked very well with silicon. Not an effective contextual that it create a spice inside, have low resistivity, very that's one of the lowest in periodic table, and it was excellent for early microfabrication use. There are tools that is based on aluminum, that electronics we see, and that as we go into smaller and good quality application, this electromagnet will lead to problems. Then the resistivity limited. When we have smaller, many properties of materials change, as well as aluminum resistivity gets limited, and it cannot handle the speed that we want now, and the performance is good. Okay. So why not any other metal? Why copper? Okay. Why people shifted copper? One is copper is having very high conductivity. It counts the effect of this resistivity, limited speed, and performance. That's fine. But there is a problem that copper is a defect in silicon and can severely degrade device performance if it diffuses into the silicon. Unlike aluminum, where small bit of diffusion was an issue, larger diffusions were an issue, or diffusion is big issue. So copper actually has a defect. It uses very low silicon and causes significant damage to device performance. And then at low temperature, we are talking about 400 degrees Celsius, because some processes or even thermal operation can be temperature, and it can diffuse through dioxide, not just silicon. So if we have silicon, and then on top of SiO2, on top of it we have copper. So it might have that this copper will actually pass through the SiO2 and into the silicon. So that's a big problem, because we are supposed to use this Si insulator, and we don't want the like silicon to mixing with copper. That's a problem, because it creates deep level traps. If you have learned, if you will see a bit of semiconductor fundamentals, you learn trap levels and all. In silicon, it creates trap levels in loss of charge. That means it is in the you can say in sense of and a place energy level where electron get or will stay there. They will get stuck there. Will actually do degradation in device operation. So we are nothing to, and so we will problem with copper get like later on fusion and all. So how it is also tackled using titanium nitride as a barrier, which is dense, and if it is dense, the copper will not pass through it, and temperature stable. So it effectively prevents copper diffusion. As well as if we use titanium nitride, it does not increase the resistance much. It is like not and they are very thin, not thick. Okay. So how is it done? Titanium nitride deposited between the internet and the silicon or silicon dioxide internet. So before depositing copper, layer of titanium will be deposited, and then it will be deposited. This ensures that we are getting the conduction from copper as well as copper remains on silicon. It does not get inside the silicon, just creating that. And there is a process, the damping process, that is due to this silicon layer with tungsten wire to a metal. So how is it done? A thin titanium is deposited over the entire surface as a diffusion barrier. Like using even nitride or titanium tungsten is used. A very thin layer, and this is done using CVD. Okay, and then copper is put, and that deposition of copper is done, and then CMP. This is magnetic. Pit kinds are all created in this. Titanium nitride is deposited, copper is deposited. The top layer is removed using mechanical, you can say, chemical mechanical polishing, and layer it is flattened, and as such we get our deep contacts. So this is a that is common for copper-based electrodes. They are used in process. Then when we're talking about metal and metal deposition, one thing we have to take care, that is sticking coefficient. That is, what is the probability that incoming ion will stick to the system deposits different. Okay. When this sticking coefficient will depend on the energy. Like if we are going for CVD, which is the thing, it may have a different coefficient, and if you are going for ion emission, it will have different sticking coefficient or have different. So it will all depend on it is a process dependent or energy dependent. How what is the energy that is being used to bombard to transfer material wafer. This is high energy or low energy wafer. We have some moderate this sputtering. We see that sticking coefficient is, but again we have to take care that along with the sticking, we all have to do these processes at lower temperature. So C is a process that is at high temperature. And if you are talking ion implantation, that is next to the surface. Deposition using an implantation is a big issue, like we cannot do. Okay. Sticking coefficient also have impact on the deposition. There are things like where low energy like CVD, ALD, high steam probability, and when we are talking about the quality of CVD and ALD is much better. Sputtering or AVD method, it has high steam probability. These are processes low energy; they are not bombarded. Whereas if we are talking about sputtering, it has moderate and can lead to lower duty, and there can be best also. There is some called as temperature. Called as temperature is used in combination, and that's why in some cases I have seen someone was asking a question some week that are we over into of see, I think you were asking what temperature or just the wafer everything like that. Yeah. So in case string, we discussed about CV, right? But in case of sputter wafer heat, as we use here in thermal evaporation also. So to counter this problem, this is the energy problem. Some heating is used, but we cannot certainly go heating all the some heating according to our need. If we are not able to film and a lot of scattering is happening, temperature helps in countering problem. Fine.
So really asking with an eye, right?
Sticking coefficient should sub all other area, like to make it not make like put much of temperature. The process we had done earlier, that is wasted. That should come.
Yes, yes.
Now something called as patterning, and this is one of the most important part and one of the most costliest part in this whole microfabrication. To understand what is pattern, okay, this pattern so a small video from YouTube. Okay, so understand it. So it is actually made, okay, using different coverings, exposing areas, and if you see the layers, whatever thing, they were matching it using the cursor and hair, right? So this is a big version of pattern lithography being used in daily life, in common life. What we see, the leaf is a miniaturized disc only. Okay, if we see this, then you see these patterns, small patterns of the tiles, the small pattern they made lithography and multiple layers of lithography that makes not a single layer. Okay, so what is a pattern transfer? It is transforming a continuous thin film. We have learned about transfer film. We have learned about if we deep cover remove the extent, we get that part like and all. But mostly or thick film for some cases. Okay, but how to pattern that? How to make source drain? How to we have like said how to open a smaller deposition areas, deposition. How to do it? Okay, this the user pattern to form the continuous film into different dimensions. This is very essential to tone or form because it's not two sets. Otherwise, we have one layer, then another layer, then layer, no interacting. This enables different conductance. So, in the same layer, some part conducting, some part insulating, and that we can do using pattern, different area for function. So, there are two types of pattern transfer. We know the pattern we have on our wafer. And the direct transfer, that is no intermediate, that is the pattern we create it on the material. Second, direct pattern transfer. That uses a direct transfer the website. That means we create the patterns on a stem or like on the video just we were using a film that already had the thing that we wanted and uniform paper uh, applied over it, and then that pattern was removed. We got a such kind of pattern and we are used to transfer onto the surfaces indirect transfer. So the difference is direct transfer. In case of direct transfer, material is directly without any layer like milling, writing, and field scribing. Okay, I use mostly laser writing. And in laser, it is done that to create the picture, and it it is similar to photolithography. We'll be saying that it just creates the pattern using laser. It is a very point using that it will create a pattern that we want to, and that will subsequent figure pattern that we. Okay, so similar to people where we are physically making the pattern, like the physical scribing is done, iron milling is done. Okay, these are simpler process. Like they use less steps. Okay, okay. But they have problem that they have vision. They might lead to substrate damage because we will have to leave and that can substrate damage as a contamination. Then in pattern, why here the thing that we are directly playing with our substrate, the main device. It is it is protect. It is getting okay. So can give some straight damage as well as condensation. Whereas if we are talking about indirect pattern transfer, so pattern transferred on an immediate layer and then the strip. So that acts as master layer, you can say, master pattern, and that master pattern can be used multiple times. Example, optical lithography is that instead of optically doing it, or uh, it is not being seen, we can higher resolution doing some optical kinds of, as well as it is highly repeatable. The same thing is fixed. We don't have, that's why it is having higher resolution, have repeatability. Disadvantage is that it's complex and it requires a lot of resource just to run the machines like optical lithography. A simple optical lithography also needs a lot of things to run, like it to pull down a compressor press to have some of pneumatic vacuums to hold the wafer and a lot of things. And if we talk about electron beam lithography, that is being done a wafer and all, so resource intensive complex. Okay, so very different. So what are techniques that are commonly used for pattern transfer of microfabrication? For direct pattern lithography or writing is serial process using iron milling, layering, sequence 1.9 or 1 or when tips are used to create. Second is printing, in which oh sorry, in which pattern is lifted somewhere over another. Or like you say, when we block print. Okay, so it is like intermold printing. EMS and mold used to transfer pattern. Second is indirect printing. So some of them are electron beam, where electron beams are used to pattern, and that is once at a time. The whole is just electron beam. One is optical beam. This is like this one. This is simpler. Like to developments on a photoresist. Photoresist, we will be talking some that this material is sensitive to the light. This is the metal has optical lithography. Then is then optical thermal transfer panning. It is a heat and all other. So we will not do too much about direct pattern transfer because that is not very common. We are talking about micro and nanofabrication. In transfer, since we are direct pattern transfer, we can go for high resolution. Okay. So what is the process? A general overview of pattern transfer. First is substrate preparation, and for this process, the substrate will be flat and filled. We cannot start structured, or even if it is there, it will be very structured like this. Okay, almost flat is a flat feature into the area that is photoresist. So on the for a liquid port that is photoresist, we are seeing the top view, and it is rotated so that this liquid spreads uniformly over the surface. Then you photo mask. This is a simple assembly. Talking in terms of lithography, a simple glass with simple soda lime glass with patterns using chromium, thin layer of chromium or tungsten. We have the digit pattern, okay, and we are using it over our wafer as this thing, okay, and we are exposing it. So where will fall? Only areas where it's not covered. So all except the covered area. And then develop those unexposed photos. See, in case we remove the photoresist, we remove it. In what case we remove unexposed area. See, there is there will be saying okay. Etching. That is, we we depict the pattern this layer. Okay. Now that pattern is now we have to make the pattern on our print we want. So we do the thin film. Okay. At last, we was left the pattern as the date to remove and we will find the structure. Anything till here? Questions? Anything? Yes. Anyone? Yes. Anyone? Hurry. Okay.
No.
Okay. So what the action of this pattern transfer? It is very important the synergy because we are going smaller structures every day. Because when even one day I heard something talking, maybe they were something talking about this one has 5 nanometer technology, another talking about that one has 10 nanometer. So even the kids, they are into small dimensions, processors and all. Okay, so we what's very small dimensions means the distribution to two different patterns can be as small as at present we have as small as 5 nanometer or 3 like 3 that's like, but 5 nanometer that's too small. Okay, we're talking about all dimensions, scaling registers. We do have cannot take this have to be made use this patch as well as if these are done sequentially one at a time, it will off. If we have processors like optical lithography on nanoprint, we are able to process 205 sometimes 1000 devices and more. In Go, we have the whole piece of mask made, whatever thickness paper, make multiple and one. Instead, we go for it. Sometimes, since we are in go for it, we might have some testing, but it takes a lot of exposure. Just take one day, it can take around 4 minutes. Think about 200 devices. Whereas if for optical it can take say 10 minutes for the whole process. After the 10 minutes, it can expand as well as 250. It is one whatever be the devices, it will take the same time. It is not on the surface, it is on the side. Now dividing with time. It may be the whole place that is 4 inches. It's the same amount of time you are making one. And that is it significantly affects the fat cost. Then is this also have application processes beyond that is MEMS. Nowadays, MEMS is a common where like physical structure for the wafer. We are not lecture throughout. Okay, but there are microprocessors. Those are very common sensors. Like if you remember gyroscope and things. Nowadays, most of the gyroscope MEMS is doing available ink tank printers, ink tank or this HP inkjet printer. Anyone which are artists kind of system where you protect is inside. Anyone print GK or
I also didn't see. I only saw it, example.
okay. If you be like mostly we are seeing that printers are late. One very first printer, a small box kind of structure containing the ink, and we insert it inside, and then it prints one.
Yes. Yes.
If you take that box, that is a MEMS. One of the things that we enough to have a good print. You know to deliver it we use like 91%. You see the difference like they will do. Right? This thing is and printing, and that's to a mass structure. But printing is very small. After that is mass structure is small feet apply, and it gives some very limited amount of whatever we want the word. So 3 colors and so that is MEMS. So we these things very common, but we don't know. Okay, then this application that like is pattern transmission like helping out of medical device. It has the pattern transfer going beyond 10. Okay, with optical fails much above it around 500 and we can optical and imprinting are there. Now just trying below 10 nano, like below 10 nano. So is to have a pattern in it to start. Okay, so what is MEMS? So in third or can say it's called as resist processing. We must have actual processing or basis, and this is of photosensitive metal or in case of we have drawn metal. Okay, so this is our this way. Are you able to what I'm trying?
Yes.
Yeah.
We have everything and we want this thing. Okay, so what is done is apply a result. Okay, then we bring a pattern over it. Say we have already that this we are coming small we are going this again we are going and when the review can become pattern fine. Okay, okay. The matter is that then this blood one. For now we are property world that whatever area you like that will lose or you are in a system. So after this not so remove, then dip into another that will resolve this area. So what will sorry, no, just a minute. So yeah, I have to draw it bigger, right? Just a minute. So till here clear. This any questions here? Any? We have the layer, okay? That has pattern. I'll make it bigger. Okay. Then we end this. We just over click for time and make it. Now, we did the exposure, and after exposure, in chemical that we call it. Okay. This dissolves, this area dissolves, and this area dissolves. Now, the area that is left that will tell this area will protect layer of the process. Now, due to chemical that is this way gold. Okay. When we do gold, we will remove this area. If gold is not dissolved in golden, okay, and we will have this matrix. And then next, remove the position and we get out desired pattern. Okay. I think how it is, right? This is the basic. Now there will be two when when we plot pattern, it can be far or near field mask will be close to a substrate. So whatever is of the pattern on the same plate, same or slight or far imaging, we have mask here and we put kind of structure so that we might be enlarge the so we have like translate environment and that sit down there. So we what is of the same field, right? Does anyone?
100 nanometers.
100 nanometers. So we address that button, it will equal to the lens and other other devices. So in general, kind of lithography tech projection lithography utilizes lens arrangement. Say it's clear, but actually we can image like we are only with stem to nano. This is suited for high large patterns. Okay. Then is particle lithography where particle is touching where inner possible. It is limited by the contact. That is, it will damage. Second thing is it cannot be replied dividend, whatever is the pattern. Then there's very much contact lithography. Like a bit that is proxy lithography, where a bit of the substance is kept so that pattern scale down to an extent. Okay? That is as well as much closer to lithography. Proxy. This is combination of. Now we are talking lithography. I have been taught about light. We will make a very theoretical. Okay. We will be doing all kind of lithium in the subsequent tool. Okay. So what kind of light source are used in lithography? Okay. One and most common simple photography is mercury wavelength. They have wavelength of 65 meter, 46 nanometer, and 250 nanometer. And if some no, it is correct to be.
This resolution.
You put lambda and all, you will be able to determine. So there are possibly given the minimum with this minimum resolve using digital set 12 something almost if we are saying minimum we can go for 50. What I am doing is like although it's practically 350 or something, you will be able to have 500 or 600. Okay. This problem with Maria that brought that don't give a single length. Filtering to be for length and as such like because but then other ones are example which are put in for is 0.3 meter 1 filter. Ones are used like the advantage is so if 11 D so lambda is so it will be better. So we can get something 96 fiber. It requires that kind of air will hot so water cooling and slide of so it becomes complex. Okay. Here two concepts are in case of optical. Okay. for this purpose, it is that we have to understand what we have to go, and if you are go for some photo dealing will also change, and of photoresist, cost of maintaining equipment have been in when this is done, okay? As well as we have to use very costly, okay? And there is more.
The reason why we line G line
It's the strum of this, no? Because like for have line pass and for this, right? Each line spectral line actually this is immense must have like that we already, but it's refer where you can find. Okay, they are related to spectral lines, and they are spectral lines. The spectral line new upon lambda that new so that you have calculated. These are how much mercury when mercury that energy we without we have data how much energy it is absorbing and releasing those. So if we see them, so I have done video about you are from in the first years of I that which the some land pendings. So get the same wave. You have the same wavelength because the electron like there's electrical come out at six levels. About quantity fixed energy level, fixed energy level. We have each at new opens, you know. Yeah, I see them. I'm missing the limitations. So fixed, we will get new cycle on the quantum level, the excited electrons. So we have like ID line and these like the electrons with. So observe the electron out of these photons. It is like there are three type of come out maybe. Okay, 3 405 is there. Okay, so we put filters to the electron except for 365. Okay, except for 365 will plus because I know perfectly that the filter those there are fields. So I'll change that field. It can be electric field and the mostly electric like the field is filter when in lithography.
Okay.
But
yes.
So like in each answer I forgot. New inside you assumptions.
lambda,
Yeah,
and the field C lambda.
yeah, because where I did.
It's well lambda.
So how we resist? So there is margin liquid that is solid. This is the thing that sensitive light, sensitive and solvent. It is the liquid solid. Make it photo. Okay. Two particle absorption. The Bird's law that absorption comes at efficiently. Devices resist. There is that the sum of absorption sensitized and reaction. So therefore the students it's directly to the surface. And we can use that law. You are going to say. Yeah. Now am I audible? Okay.
Yep.
So there are two kind of points. One is bleaching. Bleaching is sensitized. Okay. Just project specifically. But there are some non-bleaching solvent and so they are not effective. Like transparency is not effective by the because that changes it particles can be developed. Okay. So but we have two kind of material. One thing that becomes transparent and one non-bleaching not either. Okay. So there are two photos. One is positive and negative. Talking about light fire will come that we here suppose that this is reported this area and the, except for the area center I'm putting light over this. So if it is a positive resist, this area remove and what was in the main. Okay. If resist thing if it was it will get on like this. Okay. This main. Whereas if we are using negative resist, where everything is except for the area that was detected. So the area will be hard. And how it does what happens is that phone hits inside the resist and it multiple rings. As such, it's not yet to individually expose each end. Okay, so if photon is found that surrounding area will get exposed. If they said whatever value it can be a bit smaller or larger than the actual one, because boundary can also expose or may not be. Like if it is like the moving extra part, it will be hardening an extra part. If it is ready for this, all part be removed. Okay. So what are the process steps that we will be in the subsequent 2 weeks? It is wafer. Then okay, this addition guys we have covered. I will put that in the next class. Question? Anyone? Projection and why again? Okay, was twice. So there's problems I have we have. So that's how I say everyone. Or something you have to solve.
Equivalence questions are not able to because not covered, so
Okay.
able to find it.
Things actually I extract you can parts. Okay. Yeah. You can see I put answers also. Okay. Like if that solves them. Okay. Where the mask be perform lithography with some gap and projection objects by positioning the between the illumination and projection of. The answers.
Right.
Lithography there are options mind. Okay. Each of the positive negative photo. Positive field there and exposed will be removed. Positive photo find the resist and removed. Negative little tougher is next will be removed. Negative little tougher is next will be. Yeah. That's okay. We have just now that the area that gets exposed for is removed. That gets moved for negative photo remains there because it is hardening. Now let's glide to achieve a critical size of 40 nanometer, 40 nanometer, 93 nanometer. Yes. This commonly nanometer size, like nanometer. Okay. Family which of lens pattern tool for electrons tool.
Yes.
So the distance, right? Okay, let's I think I have much. Although, sir, what the process for delivery? PR is pre spool push break there is break double or what is sure. So but sir or here the photoresist we are hitting it for some time it hardens or it resist that makes it that solvent. Then we go for again and then so that the part we want to remove that is turned on the product. We'll be covering next class. This not that not I'll dive in the so any questions? Yeah.
Sir, positive negative force is commonly used in our research.
Mostly positive. More some are doing in now. So negative is preferred before it's off. We are in the opposite. We are making and then position more pattern. So in this negative, we'll see later. We are when we are stressed. When we are stressed, that if when we develop photo is becoming like this. So I think sir, it has developed where beside stress, they are like this. They are this. So this is the generalization of people. Or they can vary as some all the same and these are that happen. So if you have to deposit something over it. So it will put it like that. And even but there will be a break. Or are you understanding? Fine. Suppose that defeat a chemical with remover. It will actually some part of this because different one. Where in the so if we that our deposition, we will get our percentage. This one will be better. That's why this is very technical as lot of negative is preferred and this is one when smaller dimension as well form for where we cannot aging like adenum and DPT they may not eat whatever material that is not easy out so I will lift off. I saw PR but sensitive PR is common. So anyway we is a few different disorders. For PR is like it is cost the same piece of material. Like there are some because of SUN but you know it's too costly. It is much too PR. And the flip issue, they are very small, like they are not measured in we get they have already already 2 months have and when 8 months they have to be in normal. That is also issue. Then yeah, you have some. Okay. So we will move with orthography. I will next and we'll be going to lithography. Okay. So see you all.
Thank you very much.